Let me go into detail now to the presentation. I think I don't need to contextualize, actually. This is I think something we know very well, that in general, the global agricultural robotics market trend is increasing, and time on this. And the mushroom industry is no exception. In the Softgrip project, what we tried is to really point and target the probably most difficult part that is related to the actual picking of mushrooms. We know what are the problems related to this very challenging task, also from, let's say, the task itself, I mean, the motion capability that are required. And this is why also the dexterity, the sensitivity, and the precision the human hand is not achieved. I mean, it's not achieved by robotic platforms. But we tried. We made our efforts. Stop me.
I don't know.
Okay.
Wat u niet trap heel wrong.
So our target in this project was the development of a functionalized automatic gripper for delicate produce harvesting, powered by imitation learning-based control. What are the main elements about our system? We are aiming at low cost, first of all. Then we are taking advantage of soft materials, and that's why we are dealing with soft robotics. The idea to use soft materials in making robots instead of the traditional approach using metals or rigid materials. We are trying to use the intrinsic flexibility and safety that you can find in using soft materials. We are using intrinsic sensing, but also embodied intelligence to, as a base of our control and to simplify some of the actions so that some tasks become easier and simpler if you consider the body characteristics of your robotic device. But we are also considering materials that have been developed to be intrinsically food safe. We will see some details about that, but also with an eye to the environment with recyclability features. And also able to self-repair with the effort to minimize the maintenance of the systems. And finally, the control that is based on imitation learning, so like advanced AI technologies based on human demonstration. What is the expected impact? Of course, the first and most straightforward impact is related to enabling state-changing efficiency and increasing job quality and safety, but also science and technology. So developing and trying to introduce new technologies for delicate yet effective manipulation, even going beyond the agricultural sector, and also new techniques for heat transfer through metallurgy. And the broader terms, the extended and long-term vision would be to open new opportunities for robotic solutions in the agricultural sector, but even beyond, lowering also the barriers in adopting robotic technologies. This is the consortium, 6 partners from 5 different countries. But now let's dive into details about the Softgrip system. This is the overall architecture. Let me just introduce the overall system. So we have the core, let's say the heart of the system that is based on a soft robotic gripper. Then give details that is connected to a Cartesian robot that is installed on the cultivation shell. Then there is a vision system that is installed at the base of the gripper. It is able to acquire all the data that are then fed into the grasp planner and the grasp controller, elaborating this data and then creating a trajectory to move the Cartesian robot on mushrooms, and then the grasping commands to execute the actual grasping and uprooting of the mushroom. Okay, so starting with the gripper, we started really into details about materials. We are still having a member of the group that is based on chemistry. I mean, their expertise is on chemistry. They are synthesizing basically materials that are exactly for this purpose. We try to tailor the mechanical properties, well, actually all the properties of the material, in order to have the best material for this task. In terms of mechanical properties, we had an extensive research of something that would be able to have enough compliance to interact safely with mushrooms, but at the same time to have enough robustness and stability to have a firm grasp, stable grasp. Then we also already used materials, raw materials that are already included in the positive list of Commission regulations so that we can have directly food safety. Then we also studied the possibility to have self-feeding capability. This is what I referred to when I was speaking about low maintenance. These materials are able to self-heal when they are put in, under 120 degrees of heating for a few hours. And they are recovering exact same mechanical properties as before. And this is very good whenever you have problems with these technologies that are, by the way, based on fluids. So they are pressurized, and so the grasping is based on pressurization of these structures. If they fail, if they have a burst or whatever, they can self-heal. And finally, we also had the possibility to develop this material, a material that is partially recyclable, or at least most of it is recyclable. And Mitsui developed this procedure of glycolysis and evaporation that is able to recover most of the raw materials. Then, what about the gripper itself? So we took care about the design. Our idea was to not to go for suction cups, but try fingers. So we went for the development of a gripper that is based on 3 fingers, and it is composed of 3 subsystems. The fingers themselves, that are, of course, for a conformable and delicate yet firm grasping, but also an adaptation subsystem that is taking advantage of some software technologies, especially variable stiffness technologies, to be able to adapt to many different sizes of mushrooms they are dealing with. And finally the burst subsystem that is embedding some embodied intelligence to simplify the control and to perform the outrouting with very simple commands. We selected fluidic actuation technology, as I was mentioning. In order to do that, we designed fingers through a parametric design, but also we used finite element modeling to predict and to assess how the interaction with mushroom would be. We had the possibility to see where most of the formations are, how much is the stress that is transferred to the mushroom, and so on. Then for the adaptation subsystem, we made use of variable stiffness technologies that are able to stiffen some part of the gripper so that the same actuation trigger, that is pressure, is able to generate different kind of shapes. So it is a way of pre-shaping the gripper before it is going to interact with mushroom. And finally, we designed a helicoidal actuator for the wrist subsystem to easy the harvesting. This is more or less how the gripper looks like. We also developed the palm as an interface between the fingers and the wrist that is not displayed here, but it's at the top of it. What about sensing? Well, actually, we tried with different technologies for the proprioception, so to be able to assess how much was the bending of the system, and of course, to include this information into the control loop. We went for 2 possibilities. Piezola wires that are wires based on piezoelectric effect that are produced by Mitsui again. They are very minimally invasive because they are wires. So we can easily embed them into the bottom layer of the finger. And we are able to have some good results. I'm going to show it in a while in a video, but it is difficult to sustain accurate measurements in time. The other possibility we tried is based on a commercial solution with band-low digital back sensor. Again, it's more reliable, it's a commercial solution, but it is increasing the stiffness quite a lot. And this is something we need to cope with because, of course, it is interacting with the design of the finger itself. About exteroception, we integrated contact for sensing and specifically MEMS with quite accurate and sensible threshold to measure force. But of course, we couldn't use it, as it is commercially available because this interface would have caused damages to the mushroom. So we added some soft caps, and let's say that was the best trade-off in having good interaction without damaging the mushroom, but of course lowering a bit the force sensing, the sensitivity to the force. This is an example of the performances of the piezola sensing innovation. We are considering innovation because, again, it is based on wires, so just wires that are running along the finger. And you can see here the performances against an optical tracker. Then we attached the gripper into a robot base. The robot base is basically a Cartesian robot that is then installed into the side of the touch shells through wheels. In the robotic base, there are 5 motors. Well, main motors are 5 for the motion of the system, 2 motors for the x-axis motion, this one and this one, 2 motors for the z-axis motion, and then the y-axis motor that is installed at the base of the arm. Other 2 actuators are actually dedicated to the solution, the traditional solution of the burst. This is how the real system looks like. Then I will show you a complete video, so I'm not going into details here. Now, for the control part, I'm considering, I'm directly using the harvesting pipeline, so to show how the system works, how we designed to work. It is based on a 6-step cycle. The first one actually is executed only once, that is just to scan the entire bed. And then the other 5 steps are repeated, of course, mushroom by mushroom. Okay, so the first step is to scan the bed. The vision system is installed at the base of the gripper, and we will see that actually it is quite peculiar because it is rotating at the base of the gripper. I'm showing you a video in a while on this. The idea is that the bed is divided into slices, and slices are scanned one by one, so that there is also some overlapping, so that also the matching between the slices are then easy. The basic idea of this approach is that it's quite cheap. So we are not using laser scanning, basically with the idea to reduce the cost for that. This is how the system works. So as you can see here, the scanning is made by this RGB with that data camera. The gripper is lifted up to allow the scanning of the bed, so not to obstacle the vision. And then once the rotation is completed, the information is elaborated, and we can come up with something like this. So you have a 3D reconstruction on that map, that heat map. You have a quite accurate information about location and size, and information about the mushroom to be able to plan, to have the planning of the harvesting task. Then what about the aligning with the Softgrip? So now we have information about where are the mushrooms that should be picked up first. Okay, so we can move the gripper and use the Cartesian robot for that. But once there, we also have another feature that is the in-end camera. It is basically a camera that is installed in the palm of the gripper that is helping in the visual surveying the task, so that the gripper is guided to align in an optimal way the angle of attack. Okay, so now that we are aligned with the mushroom, what we are doing, of course, is to start with the trusting part. And for this, we need to make a step back because at the beginning of the project, we were missing all the information about how to gently deal with mushrooms. So, although at the very beginning of the project, we couldn't really have this hands-on experience because of the pandemic, but after some time we could really, and we can hear actually Chagas with this very strange gloves, sensorized gloves, to to acquire information as much as possible about the force that expert harvesters usually use in handling in this harvesting task. So we got recordings, a lot of recordings actually, related mainly to twisting and bending angles related to mushroom, and also the normal and tangential forces that are developed by each finger, or at least the three most involved fingers. What we got was related to how to combine twisting and bending so that the harvesting is correctly performed, minimizing also the possibility of damaging mushrooms and of course having successful uprooting. We also, with this data, we were able to develop a simulation framework that we used a lot, and that includes the mushroom root failure mode, so to also apply the learning techniques that we used with an imitation approach. In parallel, we also developed a dynamic model based on continuum mechanics that has been also validated through computational and hardware experiments. And we use those, of course, for developing model-based control schemes for bending, painful control, and gentle grasping. Finally, we could come up with the uprooting parts of the last part that is using all data that has been collected before. And we developed an imitation learning-based adaptive motion planner that can also take advantage and learn and to react to tactile feedback. That's why also the sensing part is online and it's having a major role. And we validated this approach also in experimental test beds. We made all the system integration at Chagas, so actually the system is here and this at this very moment under testing. Chagas also developed a new assessment method because actually what we wanted to have was something that was able to validate and evaluate the performances of our system, at least in terms of the quality of the mushroom that we were able to pick. And Ellen and the group of Chagas came out with this idea of having a way of assessment that is based on color assessment. This is using a combination of parameters. That using this equation basically gives a number that can distinguish, that can fall in three main areas. If it is lower than 5, it means that the mushroom has been very well and gently treated, and that's why here we have the high quality produced mushrooms. In between, so above 5 and below 8, we have acceptable quality, and higher than 8, we have not acceptable quality, or semi bad quality. How did we perform? Well, actually, as I said, we are still testing. We made just a preliminary campaign about testing. The successful rate seems quite good, but we had this preliminary data about this color assessment that, let us think about that we need to, improve a little bit. What are the main limitations? Well, actually, we had some some cases we were quite good in the course that we used to have. Of course, we are reporting only successful things. Gentle force, so in an acceptable domain, but some of them are, were treated, we used excessive force. The robot was not able to manage correctly the force that was exerted to the mushroom. These are some figures reporting what we are referring to when we say that there is excessive force. And there is also the discrimination between when there is a peaking force that is related to the normal force, but also if there is any sliding. Because one thing that we noticed is that when the gripper, since it's a soft gripper, is interacting with the mushroom, and when the rotation, the twisting is applied, sometimes we have sliding. This sliding, of course, sometimes may also cause bruising. And here you can see some of this result. This is the control, they are perfect. Here are some of the problems that we are